Today we will begin working with Chapter 17.1 on analytic geometry. And we're going to get into the meat of this chapter and all of the algebra and the new algebraic terminology which we'll be using for the rest of it. So the first thing to learn is that a lot of what we're working with are going to be linear equations. So a linear equation is any equation whose graphical representation can be made with a straight line. And here you have depicted several linear equations. Curved lines and wavy lines are not linear equations. They're called nonlinear equations. A very simple nonlinear equation that you can graph yourself, and I really think you should graph immediately, is y equals x squared. And that's one of the most simple nonlinear equations there is. It's a very important one. And it's the type of equation that you see all the time in the real world, but we'll discuss that more in the future. But linear equations are the building block of analytic geometry. If we don't understand linear equations, we're never going to understand nonlinear equations. And so let's work with these linear equations, knowing that they do have applicability to life. They have a lot of applicability in engineering and architecture, but they're also the building blocks of much more important and complicated graphing techniques, which are going to be so helpful to you as you progress as numerate and literate young leaders in society. Two other terms we have to be aware of in this chapter are x-intercept and y-intercept. So an x-intercept is the point on a graph where the equation intersects the x-axis. And the y-intercept is the point on the graph where the equation intersects the y-axis. So intercept just means passes through in this case, where the y-axis intercepts the equation. Lastly, in analytic geometry, as in all geometry, we have conventions for what variables are going to represent. X always represents things that go on x-axis. Y represents things that go on a y-axis. Slope is represented by the letter m, a lowercase m. And if you recall from last time, slope is the change in y over the change in x. And a way of representing this is y at time 2 minus y at time 1 over x at time 2 minus x at time 1. So let's say I have this equation graphed here, and I have x at time 2 and I have a coordinate at time 2 and a coordinate at time 1. My coordinate at time 2 is 1, 5. My coordinate at time 1 is negative 3, 2. So that is 5 minus negative 2, which is 7. And then 1 minus negative 3, which is 4. And so our slope is 7 over 4, meaning that from one point to the next on this lattice, we go up 7, 1, 2, 3, 4, 5, 6, 7, and over 4, 1, 2, 3, 4. And that would keep repeating along the slope. And this is not a reducible fraction. So let's begin with 17.1. Find an equation whose graph is the line passing through points -1, 7 and -5, -3. So first you want to pull out your graph paper and identify those 2 points, the coordinates of those 2 points mentioned, and draw a line through them using a straight edge, as I have done here. And really double check that you're doing this correctly, because you can mess yourself up real bad by getting the x and the y confused. Remember, the x comes first and then the y comes second. So -1, x, y is at 7 for that coordinate. And on the second coordinate, -5, x, and -3y. Okay, so how are we going to find the equation? So remember, the equation should be able to tell us for any number I put in for x, I can find the y, and for any number that I put in for y, I could find the x. So this might be a little bit hard to conceptualize, but just follow me through and you'll get the hang of it quite quickly. It's not so bad. Let's find the slope. So what's the slope of this line? See if you can figure it out yourself. So let's simplify this. The order that you do these in does not really matter so long as you're consistent, that this is one coordinate and that this is the second coordinate. As long as you're consistent, then your slope will be correct. But if you're inconsistent, then you'll be messing yourself up. So -3 minus 7 is -10. And -5 minus -1 is also known as -5 plus 1, which is -4. The negatives cancel out, and we are left with 10/4, which reduces to 5/2. So that should be the slope. Let's look at our graph and check it to make sure this makes sense. The equation should intersect at a integer coordinate whenever we go over 2 and up 5. So 1, 2, 1, 2, 3, 4, 5. Yep. Over 2, up 5. Up 5, over 2. Rise over run. We rise 5 and run to the right 2. Excellent. So now what do we do? How are we going to make the equation for this line? The equation for the line is not just 5/2. Why not? Because this line is also 5/2. And this line is also 5/2. And this line is also 5/2. And this one, 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 and this one. These are all lines with the same slope. So we need to specify this one somehow. This is the one which passes through -7 and -1. That's how we'll specify it. There's only one line with the slope 5/2, which passes through any of the coordinates that it passes through. So what I'm going to do is I'm going to take this coordinate and put in y and x, and then I'm going to simplify my equation. Let me show you how to do that. Y minus 7 over x minus -1 equals 5/2. And then I'm just going to simplify this into a form that I find acceptable. Now, the first form that the book simplifies it into is what's called point slope form, where we multiply both sides first by this denominator. So y minus 7 equals 5/2 times x minus -1. The reason it's called point-slope form is because in this case we have a point, a coordinate, -7 and -1 indicated in our equation, and we have the slope. So we have a point and a slope, hence point-slope form. We can convert point-slope form into standard form, which we saw right over here, standard form, without too much ado. And to do that, we're just going to try and get our x and our y on the same side. So let's distribute our 5/2 in. In 17.2, we are to find an equation whose graph is the line with slope 4 and y-intercept 0, -3. Alright, so let's mark 0, -3 as our y-intercept, and the slope of the line is 4. What does it mean for slope to be 4? I thought slope was always supposed to be y over x. Well, if we want 4 in the form of y over x, 4 is equivalent to 4 over 1. So for every 1 x, we move positive in the positive direction. We move 4 y's in the y positive direction. 1, 2, 3, 4. So there's our line. Let's see, can we put this in point-slope form? We have our slope and we have a point at 0, -3. With those two facts, we can put this in point-slope form. So here we have our equation in point-slope form. The important thing to realize is that point-slope form is always y minus the y coordinate of our point equals slope times x minus the x coordinate of our point. Now let's rearrange this equation to go in what's called the slope-intercept form. And this is probably the most commonly used form for these equations. It's the one that is called y equals mx plus b. And we'll go over that. So to do it, let's isolate the y. So here we have our equation in what's called slope-intercept form. And the reason it's called slope-intercept form is because this equation tells us what the slope is. It contains the slope as the coefficient for x, and it contains the y-intercept, not the x-intercept, the y-intercept as the second term on this side of the equation. So the y-intercept is indeed -3. So let's look over those three forms once again that these equations can take. Slope-intercept form, in which y equals mx plus b, where b is the y-intercept. Point-slope form, which gives us a point and the slope. And standard form, which is unloved by everyone. In 17.3, we are going to find the length of a segment with endpoints of -4, 3, with -4, -3, and +6, +1. So first, let's mark our endpoints. We want to find the length of this line. Before we take any step further, we need to double check that we chose our points correctly. -4 should be the x, and -3 should be y in our first coordinate. +6, +1. Good, that does look right. And now we need to find the length of this line. To do this, as I mentioned previously, we're going to form a right triangle. We know the height from the first coordinate to the second coordinate is 1, 2, 3, 4, 5. And the length of this other leg, this base leg, is, well, that's a lot to count, and I might miscount, so we should do this more mathematically. We'll subtract the first x from the second x. So -4 minus 6, which is 10. But you notice I didn't count right. What I should have done, -4 minus 6 is -10, -4. I can take the absolute values of those if I want, but we're going to square them anyway, so the negative will disappear. I'll call this line L. So we found the length of this line in a specific example. It's actually extremely intuitive. What's the general form? And this is the general form of what we did. y2 minus y1 is 4. And x2 minus x1 is 10. 10 squared plus 4 squared equals the length of our line segment.